Hello, listeners. Welcome to The Planet Scientist. Tonight we journey to the edge of the world where the sky touches the Earth with ribbons of light. We will follow the path of ancient solar whispers as they dance through space, carrying messages from our star to paint the darkness with colors that have no earthly names. In the far north, where the world grows quiet and the night stretches long, something magical happens. The sky comes alive with curtains of light that shimmer and flow like liquid starlight. These are the Aurora Borealis, the northern lights, and they carry within them one of the most beautiful stories in all of science. Close your eyes if you wish, and let yourself drift with us into this cosmic dance. Tonight, we will travel from the heart of the sun to the edge of our atmosphere, following particles of light on their 93 million mile journey to create one of nature's most breathtaking displays. This is not just a story of physics and magnetism, but of connection, the invisible threads that bind us to our star, the ancient rhythms that have been painting the polar skies for billions of years, the cosmic breath that reminds us we are all part of something infinitely vast and beautiful. Let us begin where all aurora stories must begin, not here on Earth, but in the burning heart of our sun, where the journey of light begins in the nuclear fires that warm our world and illuminate our days. The sun's gentle breath. 93 million miles away, our sun breathes. It has been breathing this way for nearly 5 billion years, in a rhythm as ancient as the solar system itself. But this is not the breath of wind or air. This is the breath of light and energy, of particles so small they are invisible to the naked eye, yet so powerful they can travel across the vastness of space to touch our world. Deep in the sun's core, where temperatures reach 15 million degrees, hydrogen atoms dance together in a fusion embrace, becoming helium and releasing energy that will journey outward for thousands of years before reaching the surface. This energy carries within it the seeds of the aurora, the potential for light that will one day paint our polar skies. The sun's surface is not smooth like a marble, but alive with activity. Magnetic field lines twist and turn, creating loops and arcs that dance across the solar disk. Sometimes these magnetic fields become tangled, stressed, and they release their energy in brilliant flares that send showers of particles streaming into space. This is the solar wind, not wind as we know it, but a river of charged particles flowing outward from our star at speeds of over 1 million miles per hour. These particles are mostly protons and electrons, the building blocks of atoms, carrying with them the sun's energy and magnetic personality. The solar wind is invisible to our eyes, but it fills the entire solar system with its presence. It carries the sun's magnetic field outward, creating what scientists call the heliosphere, the sun's sphere of influence that extends far beyond the orbit of Pluto. We live within this bubble of solar influence, bathed always in our star's gentle touch. But the solar wind is not constant. It ebbs and flows with the sun's moods, growing stronger during periods of high solar activity, gentler during the quiet times. When the sun is particularly active, it sends forth what we call coronal mass ejections, vast clouds of particles that race through space like cosmic storms, carrying with them the power to create the most spectacular auroras. These particles begin their journey in the sun's corona, the outermost layer of its atmosphere, where temperatures soar to millions of degrees. Here, the sun's magnetic field lines stretch and snap, accelerating particles to incredible speeds and hurling them into the void between the worlds. The journey across space takes time. usually 2 to 4 days for the fastest particles to travel from Sun to Earth. They ride the magnetic highways of the solar wind, invisible messengers carrying news of our star's activity to all the worlds that orbit in its light. As they travel, these particles carry with them the memory of the Sun's magnetic field, the pattern of forces that will determine how they interact with our planet when they finally arrive. They are small, smaller than atoms, but they carry within them the power to light up the sky in colors that have inspired wonder for millennia. And so they journey through the cosmic dark, these solar whispers, traveling at speeds that would carry them around the Earth's equator in less than a second, yet taking days to cross the vast gulf of space that separates us from our star. They are coming home to Earth, carrying with them the potential for one of nature's most beautiful displays, Earth's magnetic embrace. As the solar particles approach our world, they encounter something remarkable, an invisible shield that surrounds our planet like a vast protective embrace. This is Earth's magnetic field, or magnetosphere, a bubble of magnetic influence that extends far into space, shaped by the very solar wind it protects us from. Our planet is a magnet, spinning in space with a magnetic field generated deep within its molten iron core. This field creates invisible lines of force that loop out into space and back again, forming a protective barrier that deflects most of the solar wind around our world, like water flowing around a stone in a stream. The magnetosphere is not a perfect sphere, but an elongated teardrop shape, compressed on the side facing the sun and stretched into a long tail on the night side. It extends about 40,000 miles toward the sun and more than 200,000 miles away from it, a vast invisible ocean of magnetic influence that makes life on Earth possible. When the solar wind encounters this magnetic barrier, most of it is deflected away, flowing around our planet like a river around a boulder. But some particles find their way in, guided by the magnetic field lines that connect the day and night sides of our world. These particles are the ones that will eventually create the aurora. The key to understanding the aurora lies in the shape of Earth's magnetic field. Like a bar magnet, our planet has two magnetic poles, roughly aligned with the geographic poles, but not exactly. The magnetic field lines emerge from one pole, arch high above the planet, and curve back down to the other pole, creating pathways in space. These magnetic field lines act like invisible highways, guiding the solar particles toward the polar regions, where they will eventually interact with our atmosphere. The particles spiral along these magnetic pathways, following the field lines down toward the poles like beads sliding along invisible wires. As they journey along these magnetic highways, the particles are accelerated by the changing magnetic field, gaining energy and speed. They are being prepared for their moment of glory, when they will collide with the atoms of our atmosphere and transform their kinetic energy into light. The magnetosphere is constantly changing, responding to the varying intensity of the solar wind. During quiet periods, it maintains a relatively stable shape, but when a coronal mass ejection arrives, the magnetic field is compressed and distorted, creating conditions that can lead to spectacular auroral displays. These magnetic storms can last for hours or days as the Earth's magnetic field wrestles with the enhanced solar wind. During these times, the aurora can become visible much farther from the poles than usual, painting the sky in colors that can be seen from latitudes where they normally never appear. But even during quiet times, the magnetosphere is alive with activity. particles are constantly being guided toward the poles, creating a steady stream of auroral activity that varies with the rhythms of the solar wind. The aurora is not a rare event, but a constant one, always present in the polar regions, always dancing in the sky above the ice and snow. The magnetosphere is our planet's gift to the aurora, a cosmic focusing lens that takes the scattered energy of the solar wind and concentrates it into narrow bands around the magnetic poles. Without this invisible shield, the aurora would not exist, and neither would we. The ionosphere's welcome high above our heads, far above the clouds and weather, lies a region of the atmosphere that exists in a realm between Earth and space. This is the ionosphere, stretching from about 50 miles to 400 miles above the surface, where the air is so thin it would seem like vacuum to us, yet thick enough to glow when touched by particles from space. The ionosphere is named for the ions that fill it, atoms and molecules that have been stripped of electrons by the sun's ultraviolet radiation, creating a sea of charged particles that can conduct electricity and interact with magnetic fields. This is the theater where the aurora performs, the stage where solar particles transform into light. During the day, the ionosphere is energized by solar radiation, its ions dense and active. But at night, in the polar regions, it becomes a different place, quieter, more receptive to the particles that have traveled so far from the sun. Here, in the darkness above the ice, the conditions are perfect for the aurora to begin. The solar particles, guided by Earth's magnetic field, arrive at the ionosphere with tremendous energy. They have been accelerated to speeds of thousands of miles per second, carrying with them the kinetic energy that will soon become light. As they enter the thin atmosphere, they begin to collide with the atoms and molecules they encounter. The most common collision is with oxygen atoms, which make up about 20% of the atmosphere even at these great heights. When a high-energy particle from the sun strikes an oxygen atom, it transfers its energy to the atom's electrons, boosting them to higher energy levels, a process called excitation. But electrons don't like to stay in these high-energy states. They want to return to their ground state, their natural energy level, and when they do, they must release the extra energy somehow. That energy is released as a photon, a particle of light, and it is this light that creates the aurora. The color of the light depends on which type of atom is struck and how much energy is involved. Oxygen atoms, when struck by moderate energy particles, emit a distinctive green light, the most common color of the aurora. This green light has a wavelength of 557.7 nanometers, a color that human eyes are particularly sensitive to. When the solar particles have even more energy, they can strike oxygen atoms harder, exciting them to even higher energy levels. When these highly excited oxygen atoms return to their ground state, they emit red light, creating the crimson curtains that sometimes dance at the very top of the auroral display. Nitrogen atoms, the most common component of our atmosphere, also participate in the auroral dance. When struck by solar particles, nitrogen can emit blue and purple light, adding cooler tones to the aurora's warm greens and reds. These blues and purples often appear at the lower edges of the aurora, where the atmosphere is slightly denser. The ionosphere is layered with different densities of atoms at different altitudes. This creates a natural sorting system for the aurora, Red light tends to appear at the highest altitudes, where the atmosphere is thinnest, while green light dominates in the middle altitudes, and blue and purple appear lower down. The process happens continuously, but not uniformly. The solar wind varies in intensity, the magnetic field fluctuates, and the ionosphere itself changes with the time of day and season. This creates the dynamic, ever-changing nature of the aurora, sometimes a gentle glow, sometimes dramatic curtains of light that seem to dance across the entire sky. Each photon of auroral light represents a moment of connection between our planet and our star. A single particle from the sun's surface transformed into visible light in our atmosphere, multiplied billions of times over. These individual moments of light create the spectacular displays that have captured human imagination for millennia. The polar dance. The aurora does not appear randomly across the sky, but follows an ancient pattern written in the language of magnetism. Like a cosmic spotlight, Earth's magnetic field focuses the solar particles into two glowing ovals that circle the magnetic poles, creating what scientists call the auroral zones. In the north, this oval typically passes through northern Alaska, northern Canada, southern Greenland, northern Scandinavia, and northern Siberia. In the south, a similar oval circles the Antarctic continent. These auroral zones are where the magic happens most consistently, where the aurora dances almost every night when the sky is dark. The auroral ovals are not fixed in place, but expand and contract with the solar wind's intensity. During quiet periods, the ovals are relatively small and positioned closer to the magnetic poles. But when the solar wind strengthens, the ovals expand outward, bringing the aurora to latitudes where it is rarely seen. This is why the aurora appears more frequently in places like Fairbanks, Alaska, or Tromsø, Norway, than in more southerly locations. These cities sit beneath the typical position of the auroral oval, in the sweet spot where the magnetic field lines guide the solar particles down to the atmosphere. The aurora is not a solid curtain of light, but a dynamic, flowing phenomenon. It appears as shimmering bands, dancing columns, and rippling sheets of light that seem to move with a life of their own. This movement is caused by the constantly changing magnetic field and the varying intensity of the solar wind. Sometimes the aurora appears as a gentle arc stretching across the northern horizon, so faint it might be mistaken for distant city lights. Other times, it erupts into spectacular displays that cover the entire sky, with curtains of light that seem to reach down toward the earth, rippling and folding like silk in a gentle breeze. The aurora has many forms, each with its own character and beauty. The most common is the arc, a gentle curve of light that follows the magnetic field lines across the sky. When the solar wind intensifies, these arcs can develop into bands, with multiple parallel lines of light stretching across the heavens. During the most active periods, the aurora can take on more dramatic forms. Curtains of light appear to hang from the sky like luminous drapery, folding and unfolding in slow hypnotic rhythms. Columns of light shoot upward from the horizon, sometimes reaching the zenith and beyond. One of the most spectacular forms is the corona, when the aurora appears directly overhead, with rays of light radiating outward from a central point like the spokes of a cosmic wheel. This happens when the observer is looking directly up along the magnetic field lines, creating a perspective effect that makes the aurora appear to converge at a single point in the sky. The aurora is most active during the hours around midnight, when the observer is on the night side of Earth facing away from the sun, but it can appear at any time during the long polar nights, painting the darkness with colors that seem to pulse with the heartbeat of the planet itself. The intensity of the aurora follows the 11-year solar cycle, waxing and waning as the sun's activity increases and decreases. During solar maximum, when the sun is most active, the aurora can be seen at latitudes much farther from the poles than usual, sometimes appearing as far south as the northern United States or northern Europe. But even during solar minimum, the aurora never disappears entirely. It continues its gentle dance around the poles, a constant reminder of the invisible connection between our world and our star. A beautiful manifestation of the cosmic forces that shape our planet's environment. The colors of wonder. The aurora paints the sky with colors that seem to come from another world, hues that have no earthly equivalent, lights that dance between the familiar and the magical. Each color tells a story of atomic interactions, of energy levels and electron transitions, of the invisible made visible in the theater of the night sky. Green is the heart of the aurora, the most common and recognizable color of the northern lights. This ethereal green glow comes from oxygen atoms about 60 miles above the Earth's surface, where the atmosphere is thin enough for the atoms to emit light efficiently, yet thick enough to provide abundant targets for the solar particles. The green light has a wavelength of 557.7 nanometers, right in the middle of the visible spectrum, where human eyes are most sensitive. This is not coincidence. Our eyes evolved under the light of our sun, and they are perfectly tuned to detect the colors that matter most for life on Earth. The green of the aurora is the same green that plants use to capture sunlight, the same green that signals life and growth. Above the green, in the highest reaches of the atmosphere where the air is thinnest, oxygen atoms dance a different dance. Here, where the solar particles have more energy and the collisions are more intense, oxygen emits a deep red light that creates the crimson curtains sometimes seen at the top of auroral displays. This red light is rarer than green, appearing only during the most intense geomagnetic storms, when the solar particles penetrate deep into the atmosphere with tremendous energy. It creates some of the most spectacular auroral displays, with blood-red curtains that seem to reach down from the heavens themselves. Nitrogen, the most abundant gas in our atmosphere, adds its own colors to the auroral palette. When struck by solar particles, nitrogen atoms can emit blue and purple light, creating the cooler tones that often appear at the lower edges of the aurora. These colors are less common than green and red, but they add depth and complexity to the auroral display. The blue light from nitrogen has a wavelength of about 470 nanometers, while the purple light is a mixture of blue and red wavelengths. These colors often appear as a subtle underglow beneath the more prominent green curtains, adding richness and depth to the overall display. Sometimes, rarely, the aurora can appear white or yellow. These colors are usually the result of multiple emission lines combining, creating a complex mixture of wavelengths that appears white or pale yellow to the human eye. White auroras are often seen during very intense displays when all the atmospheric gases are being excited simultaneously. The colors of the aurora are not static but constantly changing, shifting and flowing as the solar wind varies in intensity and the magnetic field fluctuates. A green arc might suddenly develop red fringes, or blue undertones might appear and disappear like whispers in the light. The human eye sees these colors differently than cameras do. Long exposure photographs can capture faint auroras that are barely visible to the naked eye, while very bright displays might appear almost white to human observers, even though they are actually emitting distinct colors that cameras can separate and record. The colors also vary with location and altitude. Observers at high latitudes might see predominantly green auroras, while those at lower latitudes during strong geomagnetic storms might see more red. The altitude of the observer also matters. What appears as a green arc from the ground might show red fringes when viewed from an airplane. Each color in the aurora is a fingerprint of the atoms that created it, a signature of the energy levels and electron transitions that transform the kinetic energy of solar particles into the visible light that dances across the polar sky. In these colors, we see the very atoms that make up our atmosphere, glowing with the energy of our star. Ancient lights, ancient stories. Long before science explained the aurora's true nature, human beings looked up at the dancing lights and created stories to make sense of the magic they witnessed. These ancient tales, passed down through generations, reveal how profoundly the aurora has touched the human imagination throughout history. The Inuit people of the Arctic, who live beneath the aurora's most frequent displays, have many names for the northern lights. They call them Aksarnurk, the dance of the spirits. In their traditions, the aurora represents the souls of the departed, playing a cosmic game of football with a walrus skull across the sky. Some Inuit stories tell of the aurora as a bridge between the world of the living and the world of the dead, a pathway of light that souls travel when they leave the earth. The dancing lights are said to be the spirits of children who died in birth, forever playing in the sky, their joy visible as shimmering curtains of light. The Sami people of northern Scandinavia, Europe's indigenous Arctic inhabitants, have their own rich tradition of aurora legends. They call the lights Reventule, firefox flames. According to their mythology, a magical Arctic fox runs so fast across the snow that its tail brushes against the mountains, sending sparks flying into the sky. In some Sami stories, the aurora is the energy of the departed, but not in a frightening way. Instead, it represents the life force of ancestors watching over their descendants, their presence made visible in the dancing lights. The aurora is a comfort, a reminder that death is not an ending but a transformation. Norse mythology offers another perspective on the northern lights. The Vikings believed the aurora was the reflection of light from the shields and armor of the Valkyries, the warrior maidens who carried fallen heroes to Valhalla. The shimmering lights were the glint of celestial weapons as the Valkyries rode across the sky. Some Norse tales describe the aurora as Bifrost, the rainbow bridge that connects Midgard, the world of humans, to Asgard, the realm of the gods. The dancing lights were seen as the gods traveling between worlds, their divine presence made visible in the polar sky. In Finnish mythology, the aurora is called Reventule, the firefox flames, similar to the Sami tradition. But Finnish stories also speak of the aurora as the breath of the Arctic fox, visible as it runs across the snow-covered landscape. The lights appear where the fox's breath meets the cold air, creating a magical display that connects the earthly and divine realms. Native American tribes have their own aurora stories. The Menominee people of Wisconsin believe the aurora represents the torches used by great fishermen spearing fish at night. The Maka tribe of the Pacific Northwest sees the aurora as the dance of the whale spirits, celebrating in the sky above the ocean. Even cultures far from the typical auroral zones have aurora legends. In medieval Europe, the rare appearances of the aurora at lower latitudes were often interpreted as omens, sometimes good, sometimes bad. The dancing lights were seen as armies of angels and demons battling in the sky, their conflict visible as shimmering curtains of light. These ancient stories share common themes. The aurora as a bridge between worlds, as the presence of spirits or ancestors, as a manifestation of divine or magical forces. Across cultures and continents, humans have looked up at the dancing lights and seen something sacred, something that connects them to forces larger than themselves. Modern science has given us a new story of the aurora, one of solar particles and magnetic fields, of ionosphere and electron transitions. But this scientific understanding doesn't diminish the magic, it adds to it. The aurora is still a bridge between worlds, connecting us to our star and to the cosmos beyond. It is still the dance of spirits, the spirits of atoms and electrons, of magnetic fields and solar winds. The ancient stories remind us that the aurora has always been more than just a physical phenomenon. It is a source of wonder, a connection to the cosmos, a reminder of the magic that surrounds us every day. In the dancing lights, we see not just the interaction of particles and fields, but the eternal human desire to find meaning in the beauty of the natural world. The aurora's silent song. For centuries, people living beneath the aurora have reported something remarkable. The lights seem to make sound, not the crash of thunder or the whistle of wind, but something subtler, more mysterious. They describe crackling sounds like static electricity or gentle rustling like silk moving in a breeze. Scientists have long debated whether the aurora actually produces sound. The lights occur at altitudes where the atmosphere is far too thin to carry sound waves in the traditional sense. At 60 miles above the Earth's surface, the air is so rarefied that sound, as we understand it, cannot exist. Yet the reports persist, particularly from indigenous peoples who have lived with the aurora for generations. They describe sounds that seem to come from the lights themselves, crackling, rustling, whooshing sounds that accompany the most intense displays. These sounds are typically heard only during the most active auroral periods, when the lights are brightest and most dynamic. Recent research has suggested that the aurora might indeed produce sound, but through a mechanism different from what we typically think of as sound. The rapidly changing magnetic fields associated with auroral activity might create electrical charges in objects on the ground, metal structures, trees, even human hair. When these charges discharge, they could produce tiny sparks that create the crackling sounds reported by aurora observers. The sounds would be very quiet, barely audible, and would occur primarily during the most intense geomagnetic storms when the magnetic field changes are most rapid. This would explain why the aurora's sounds are so rarely heard and why they seem to come from the lights themselves. The observer on the ground would experience the electrical discharge at the same time they see the aurora, creating the impression that the lights are making sound. Whether or not the aurora actually produces sound, there is no question that it has a rhythm, a pattern of movement that suggests music. The lights dance and flow in ways that seem almost choreographed, speeding up and slowing down, brightening and dimming in patterns that feel musical to the human eye. Time-lapse photography reveals the aurora's rhythmic nature even more clearly. The lights seem to pulse with a heartbeat, expanding and contracting in waves that ripple across the sky. This rhythm is driven by the varying intensity of the solar wind and the oscillations of Earth's magnetic field. The aurora's movement is hypnotic, almost meditative. Observers often report losing track of time while watching the lights, feeling as though they are witnessing something alive, something that breathes and moves with conscious purpose. The lights seem to respond to the observer's attention, brightening when watched, dimming when ignored. This responsiveness is, of course, an illusion. The aurora is driven by solar and magnetic forces, not by human observation. But the illusion is so compelling that it has become part of aurora folklore across many cultures. The lights are seen as conscious beings, spirits, or ancestors who acknowledge the presence of the living. The aurora's silence is as important as any sound it might make. In the vast quiet of the polar night, with no wind and no sound except the distant crack of shifting ice, the aurora dances in perfect silence. This silence is profound, almost sacred, adding to the sense of otherworldliness that surrounds the auroral experience. In this silence, observers report feeling a deep connection to the cosmos, a sense of being part of something vast and eternal. The aurora becomes not just a visual experience, but a meditation, a reminder of the quiet majesty of the universe and our small but significant place within it. The silence allows the aurora to speak in a different language, not of words or sounds, but of light and color, of movement and stillness, of the eternal rhythms that govern the cosmos. In the silence, we can hear with our eyes, listening to the story the aurora tells without words. Chasing the lights. In recent decades, a new tradition has emerged in the polar regions. The practice of aurora hunting, where people from around the world travel to the far north in hopes of witnessing the dancing lights. They come with cameras and warm clothing, with patience and hope, seeking a connection to something ancient and beautiful. The aurora hunters wait in the darkness, often in temperatures far below freezing, scanning the northern horizon for the first signs of light. They check aurora forecasts, monitor solar activity, watch for clear skies. The hunt requires patience, dedication, and a willingness to surrender to nature's rhythms. Some travel to Iceland, where volcanic landscapes create dramatic foregrounds for the dancing lights. Others journey to northern Norway, where the aurora appears over snow-covered mountains and frozen fjords. Alaska, Canada, and Siberia all have their devotees, each location offering its own unique perspective on the celestial display. The best time for aurora hunting is during the long polar nights, from September to March, when darkness extends for many hours and the lights have a canvas on which to paint. But timing is only part of the equation. The aurora hunter must also hope for clear skies, solar activity, and the mysterious alignment of factors that create the most spectacular displays. Modern technology has made aurora hunting more accessible. Smartphone apps provide aurora forecasts based on solar wind data and magnetic field measurements. Cameras with long exposures can capture colors and details invisible to the human eye. Social media allows aurora hunters to share their experiences in real time, creating a global community of light chasers. But the essence of aurora hunting remains unchanged from ancient times. It is still about standing beneath the night sky, feeling small and significant at once, waiting for the universe to put on its light show. The cold, the darkness, the uncertainty, all are part of the experience, making the moment when the lights appear even more precious. When the aurora finally appears, aurora hunters often report a profound emotional response. Some weep, some laugh, some stand in silent awe. The lights seem to touch something deep within the human psyche, triggering emotions that are difficult to name but impossible to deny. The aurora reminds us of our place in the cosmos, of the vast forces that shape our world, of the beauty that exists beyond the everyday concerns of human life. It is a reset button for the soul, a reminder of what matters, a moment of transcendence in an increasingly complex world. Aurora hunting has become a form of pilgrimage, a journey to the edge of the world in search of something that cannot be bought or manufactured, a genuine encounter with the sublime. In an age of virtual experiences and manufactured entertainment, the aurora offers something authentic, unpredictable, and profoundly real. The lights do not perform on command. They appear when solar and magnetic conditions align, regardless of how far someone has traveled or how long they have waited. This unpredictability is part of their magic, a reminder that some things cannot be controlled, only witnessed with grace and gratitude. Each aurora is unique, never to be repeated exactly. The specific configuration of solar wind, magnetic field, atmospheric conditions, and observer location creates a one-time-only display. This ephemeral quality makes each aurora precious, a gift from the universe that exists for a moment and then is gone forever. The aurora and science. While ancient peoples explained the aurora through mythology, modern science has revealed a story equally wondrous, one of electromagnetic forces, particle physics, and the intricate dance between our planet and our star. The scientific understanding of the aurora has deepened our appreciation rather than diminished its magic. The systematic study of the aurora began in earnest in the 18th and 19th centuries as scientists began to recognize patterns in when and where the lights appeared. They noticed the connection to magnetic disturbances, the way compass needles would fluctuate wildly during intense auroral displays. In 1859, a massive solar storm created auroras visible as far south as the Caribbean and Hawaii. Telegraph systems failed worldwide, and the auroral glow was so bright that people could read newspapers by its light at midnight. This event, known as the Carrington Event, demonstrated the aurora's connection to solar activity and sparked serious scientific interest. Norwegian scientist Christian Birkeland conducted groundbreaking experiments in the early 20th century, using magnetic fields and electron beams to create miniature auroras in his laboratory. His work laid the foundation for our modern understanding of how charged particles interact with Earth's magnetic field. The space age brought new tools for studying the aurora. Satellites positioned above Earth's atmosphere could observe the auroral ovals from above, revealing their true extent and behavior. Rockets carrying instruments through the aurora provided direct measurements of the particles and fields involved. Today, networks of ground-based cameras and magnetometers continuously monitor auroral activity worldwide. Scientists can track solar wind conditions in real time, predict when auroras will occur, and study the complex physics of how energy from the sun is transferred to Earth's atmosphere. The aurora is not just a beautiful light show, it is also a window into fundamental processes that occur throughout the universe. The same physics that creates auroras on Earth also operates on Jupiter, Saturn, and other magnetized planets. The aurora teaches us about how stars and planets interact across cosmic distances. Studying the aurora has practical applications as well. The same solar storms that create spectacular auroras can also disrupt satellite communications, damage power grids, and interfere with GPS systems. Understanding the aurora helps us predict and prepare for these space weather events. Scientists have discovered that the aurora is connected to other atmospheric phenomena in complex ways. The energy deposited by auroral particles affects atmospheric chemistry, temperature, and circulation patterns. The aurora is part of a larger system that couples the sun, Earth's magnetic field, and our atmosphere into one interconnected whole. Modern research continues to reveal new aspects of auroral physics. Scientists study the different types of aurora, from the common diffuse glow to the dramatic discrete arcs, from the pulsating patches to the rare Steve phenomenon, a purple ribbon of light that appears at lower latitudes during strong geomagnetic storms. Each new discovery raises new questions. Why do some auroras pulsate? What creates the fine structure visible in high-resolution images? How exactly does energy from the solar wind get transferred to the particles that create the lights? The aurora remains a subject of active research, still revealing its secrets after centuries of study. The scientific understanding of the aurora does not diminish its wonder, it enhances it. Knowing that the green light comes from oxygen atoms 60 miles overhead, that those atoms were excited by particles that traveled 93 million miles from the sun, that the whole process is orchestrated by invisible magnetic fields. This knowledge makes the aurora even more miraculous. Science has revealed that we are witnesses to one of the universe's most elegant processes, the transformation of solar energy into visible light through the medium of Earth's atmosphere and magnetic field. The aurora is proof that the universe is both comprehensible and beautiful, that understanding and wonder can coexist perfectly. The aurora's gift. What does the aurora teach us? What gift does it offer to those who witness its dance? Beyond the physics and the folklore, the aurora carries lessons about life, about change, about our place in the cosmos. The aurora teaches patience. It cannot be rushed or commanded. It appears in its own time, following rhythms set by the sun and Earth's magnetic field. Those who would see it must wait with open hearts, surrendering control, accepting that some gifts come only to those who are willing to receive them on nature's terms. The aurora teaches humility. Even the most spectacular display is caused by particles so small they are invisible, following forces we cannot see, obeying laws written into the fabric of reality itself. We did not create the aurora, cannot control it, can only witness it with gratitude and wonder. The aurora teaches connection. Every photon of auroral light represents a moment of contact between our world and our star, a reminder that we are not isolated but part of a vast cosmic system. The same atoms that glow in the aurora flow through our bodies, connecting us to the stars and to each other. The aurora teaches transformation. The solar particles that create it have traveled millions of miles, changed form multiple times, interacted with magnetic fields and atmospheric atoms, and finally become light. Like the particles in the aurora, we too are constantly transforming, becoming something new while remaining ourselves. The aurora teaches presence. When watching the lights dance, observers report losing track of time, becoming fully absorbed in the moment. The aurora pulls us out of our heads and into our senses, reminding us that the present moment is where life actually happens. The aurora teaches beauty, not beauty as decoration or luxury, but beauty as a fundamental quality of existence. The aurora is beautiful for no reason, serves no practical purpose for human life, exists simply because the laws of physics and the geography of our planet make it possible. Its beauty is gratuitous, a gift from the universe. The aurora teaches perspective. Standing beneath curtains of light that stretch from horizon to horizon, we feel both infinitesimally small and profoundly significant. Small because we are tiny specks on a planet orbiting an average star in an unremarkable galaxy. Significant because we are the part of the universe that can witness this beauty, understand it, and find meaning in it. The aurora teaches wonder. In an age of explanations and analysis, when everything seems knowable and nothing seems mysterious, the aurora reminds us that the universe is still capable of taking our breath away. Wonder is not the absence of understanding, but the recognition of beauty and complexity that understanding reveals. The aurora teaches impermanence. Each display is unique and temporary, never to be repeated exactly. This impermanence makes each aurora precious, teaching us to appreciate beauty while it lasts, to hold experiences lightly, to accept that all things pass and that this passing is part of their beauty. The aurora teaches gratitude. We did nothing to earn the right to witness it. We simply had the good fortune to be born on a planet with a magnetic field and an atmosphere, orbiting a star that breathes solar wind. The aurora is a reminder that much of what makes life beautiful is given freely, requiring only that we be present to receive it. These lessons are not explicit. The aurora does not speak in words, but they are there for those who are willing to receive them, written in light across the polar sky, offered freely to anyone who takes the time to look up in wonder. The eternal dance. As our journey comes to a close, the aurora continues its eternal dance above the poles, sometimes bright and dramatic, sometimes a gentle glow, but always present, always connecting us to our star and to the cosmos beyond. Tonight, you have followed particles of solar wind on their journey from the sun's surface to Earth's atmosphere, from invisible energy to visible light, from cosmic forces to human wonder. You have seen how science and story interweave, how understanding enhances rather than diminishes magic. The aurora has been dancing in Earth's skies for billions of years. Since our planet first developed its magnetic field and atmosphere, it danced above the dinosaurs, above the first humans, above all the civilizations that have risen and fallen. It will continue dancing long after we are gone, a permanent feature of our planet's interaction with its star. But the aurora is also intensely personal. Each time someone witnesses the dancing lights, they become part of a tradition stretching back thousands of years, joining countless other humans who have looked up at the polar sky and felt their hearts expand with wonder. The aurora reminds us that we live in a remarkable universe, on a remarkable planet, at a remarkable time. We are here, now, able to witness these lights, to understand their causes, to feel wonder at their beauty. This is not ordinary. This is miraculous. As you go about your days, remember the aurora. Remember that invisible forces surround us constantly, that beauty exists at every scale, that the universe is always dancing even when we're not watching. The aurora teaches us to look up, to notice, to be present to the wonder that surrounds us. The sun is rising now over the Arctic, and the aurora must fade, but it does not disappear. It simply becomes invisible in the daylight. Tonight it will return, dancing above the poles, painting the sky with colors from another world, continuing its eternal conversation between Earth and Sun. Thank you for journeying with us tonight through the story of the Aurora Borealis. May you carry its lessons with you: patience, humility, connection, transformation, wonder. May you remember that you are part of this cosmic dance, that the same atoms that glow in the aurora flow through your body, that you are stardust witnessing stardust. Until the next time the lights dance across the polar sky, until the next time you look up in wonder at the universe's beauty, may you find peace in the knowledge that the aurora is always there, always dancing, always connecting us to something larger than ourselves. Good night, aurora hunters. Good night, cosmic dancers. Sleep well beneath the stars. Thank you, my listener, for spending this quiet moment with me. Until next time, sleep well and stay curious.